Okay, we have looked for the past few days at total work that's being done. So we're going to do the same thing, but we're going to add one more thing to that. We're going to set it equal to a change in kinetic energy. So before I do that, let's talk about what kinetic energy is, and it's the energy of motion. And you probably know about potential energy too, is the energy of gravitational, like height or elasticity, but let's focus on kinetic energy right now. The formula to do this is 1/2 times the mass of the object times the velocity of the object squared. And if you do the mass in kilograms and you do the velocity in meters per second, you will get units of joules. So energy and work are the same thing, really. So just to explore that very quickly, we have a 7-kilogram bowling ball moving at 3 meters per second, and wondering how much kinetic energy that's going to have. And if you had a little ping pong ball, how fast would it have to go to get that same amount of kinetic energy? So let's do the bowling ball. We would basically say 1/2 times 7 kilograms times 3 meters per second, and we would square that. And the answer would be in joules. I have to apologize, I do not have a calculator here, so you're going to have to do the calculation, but just, obviously pop that into your calculator. Now, if I wanted to know how much fast that the ping pong ball would have to go, I'd say, well, if I want that many joules of energy, I'm going to have to take that ping pong ball, which is in grams, make sure it's in kilograms, and we would have to find out how fast it would go if I wanted the same amount of energy in both things. So again, you could calculate the number of joules, set it down here if you want to have that same energy, go through and calculate the velocity, how fast would it have to go. And I don't have that answer, but it'd have to go really, really fast to have that same amount of energy. Okay, so what are we going to do with that? Well, what we're going to do is we're going to do the same problems we were doing before. And what we're going to do is to simply set it now equal to a change in kinetic energy, which is going to be our final velocity of the object squared minus 1/2 mv naught squared, the initial velocity squared. So the change in kinetic energy, it's always important to go final minus initial. You should be pretty used to that now. So we're going to take last chapters, we're going to take this first section of the new chapter, and now we're going to add to it this idea of the work is going to change the velocity, which shouldn't be too new an idea because we looked at the net force causing an acceleration, which of course is just a change in velocity. Okay, so we're going to kick a sled. I don't know why you'd kick a sled, but push a sled maybe. And we're going to push it or kick it that way. We're going to give it an initial velocity here of 2.2 meters per second. And we're wondering, well, how far will it go before it stops? All right, so that's its change in velocity right there. We've talked about this. Why is it fun to slide or go sledding? And that's because the coefficient is pretty low. So here's our free body diagram. F sub n, F sub g, F sub k, that's it. We've already given it this little push. So we're going to go 10 kilograms times 9.8, 98 newtons. F sub n will be 98 newtons. And so our net work, what work is being done here? Now we just did a lot of problems where there was an applied force at an angle and all this stuff, and there still could be. Somebody's pushing or pulling the sled along the ground. But really what's happening at this picture is that the sled was given a 2.2 meters per second velocity, but after that nobody was pushing or pulling on it. So the only work that's being done here is friction work. That's it. And so, myself a little more room here, I'm going to talk about the work done by friction. And what I'm going to do to get friction is I'm going to take that 98 newtons, that's my F sub n, right? I'm going to multiply it by 0.1, and that will be my F sub k. And the work that it does is the distance. So now I've done the work done by friction, and it is going to be negative work because the sled is going to the right, friction's acting to the left, it'll be negative work. All right, we're going to set that equal to the change in kinetic energy. Well, the final velocity is 0. So the kinetic energy will be 0. If I do 1/2 times the mass times 0 squared, it's 0. I'm going to subtract the kinetic energy of, I am running out of room here. I'm going to subtract the kinetic energy it initially had, which was 2.2 meters per second. I'm going to square that times 10 times 1/2. And so take a minute to do this. They're both negative, so just eliminate that. Take a minute to calculate that before you go on to the next slide and talk about it with people and come to an agreement on how far it would go. So you've got 9.8 on this side right here. So you'd have basically 5 times 2.2 squared divided by 9.8, and that would be your distance. So just kind of agree on what that would be. Okay, look at one more here, and then hopefully you can do a little bit of your work. I've got a 10 kilogram cart pushed from rest by 250 Newton force against a 50 Newton friction force over a 10 meter distance. All right, well, this is going to be an idea where we have a 250 Newton force, a 50 Newton frictional force. We have our F sub N, our F sub G. Now, I could just go 250 minus 50 and do 200 newtons here. If you wanted to do them separately, you certainly could do them separately. I think I'll go ahead and, because the question is saying how much work is done by each force, I'll do them individually, but you could make it a little quicker. So I'm going to go 250 newtons of force. The box is going to be moving that direction. Times 10 meters. Oh, don't need a calculator, yay. This is going to be positive work because the box is going in that direction and we're pushing in that direction. We have a 50 Newton force that is also over 10 meters. But of course, this is going to be a negative. And so we have 2,000 joules, which is net work. And then, so those are just like the problems we've been doing. The last question here is, how fast is it moving at the end of the 10 meters? Well, it starts from rest, and we want to know how fast it's going. I'm going to take the net work, and I'm going to set it equal to the change in kinetic energy. So I'm going to go 2,000 joules is equal to, it's a 10 kilogram cart. And I don't know how fast it goes, the final. But I do know that it starts from rest. So that whole thing is 0. It's all just 0. So I'm going to go 2,000 times 2, so 4,000, divided by 10, so 400, square root of that. Okay? And that will be your final velocity. So really we're just adding in one little extra chunk, and that is, hey, now that we have the work, we have the total work, no matter how you do it, from all those problems we've just done, we're going to set that equal to the change in kinetic energy, 1/2 mv squared final minus 1/2 mv squared initial. And that's it. So try some of the problems on the board, and we will go over those tomorrow.